Assalamu alaikum students, welcome to my channel Physics with Hasnain. Today our topic is probability density or Boltzmann distribution function and canonical ensemble. We will calculate probability that a small system has energy epsilon which is thermally in contact with a large reservoir. We will also see what is meant by famous Boltzmann distribution function and how to write probability density in terms of partition function. We are going to calculate probability distribution in canonical ensemble. Canonical ensemble partitions all accessible microstates into sets, each corresponds to a specific energy. This ensemble is suitable for a subsystem thermally connected to a large reservoir and can exchange energy with it, as you can see here. However, transfer of particles is prohibited. Consider d gamma s is the volume of phase space representing states of subsystem with energy epsilon s. And delta gamma, this should be like gamma r, is the total volume of phase space of the reservoir. Therefore, total accessible region of the phase space corresponding to energy epsilon s of the subsystem is delta gamma T for total and epsilon s energy is given by d gamma s multiplied by delta gamma r. We have multiplied both because for each state of the subsystem there are all possible states of the reservoir. We ask now for the probability d omega s that the subsystem is in the volume d gamma s of the phase space, or in other words, have the energy epsilon s because these two conditions means same. This d omega is proportional to this delta gamma T epsilon s. This T epsilon s is written in subscript. These are not multiplying with delta gamma. Now we write here d omega s equal to C constant of proportionality, where omega is the probability that the subsystem has one of the energy from possible range of energies. This should be 1, we will see it later. We want equation of the form d omega s equal to rho d gamma s, where this is rho, where rho is probability density of Boltzmann distribution function, which is what we need. But to attain this equation, we first have to expand natural logarithm of and delta gamma are as a function of total energy minus energy of subsystem. E is the total energy, and when we extract energy of the subsystem, we have E minus epsilon R, which is the energy of the reservoir. If we expand it in Taylor series, we have up to so on. Multiply both sides with Boltzmann constant Kb, we have Kb uh, this is S, where Kb is equal Kb natural logarithm of delta gamma R E is equal to entropy of the reservoir. Put this value in the above equation, we get now this equation can be solved and written as we can solve the above series like this because partial S by partial E is equal to 1 over T, which we have put in the second term, while the third term is written due to partial S by partial T is equal to Cv divided by temperature T, where Cv is heat capacity at constant volume and partial E by partial T is equal to heat capacity. These three formulas are used to attain the equation of the form like this. Now we know that T multiplied by heat capacity is approximately equal to N K P T, which is the in total energy of the system if capital N is the total number of particles in both subsystem and reservoir, and similarly Es is N K B T, where small n is the number of particles in the subsystem. If uh, n is very smaller than capital N, we can conclude ES epsilon s would be very very smaller than total energy. So we can neglect higher order terms and we are left with taking exponential on both sides. We have e to the power minus epsilon s divided by k b t. Put in equation 1, here we have this is this is equation 1 and this is equation 2. We put the value of delta gamma r in equation 1 and we obtain the form of equation 2. We get v equal this to another constant a b omega s equal to this is equation 3 and here a is equal to c into e to the power s r divided by kp. Comparing equation 2 and 3, here we have equation 2. You can see equation 2 and equation 3 are of the same look and we can compare them and obtain the value of rho. So the value of rho is equal to a e to the power minus epsilon s divided by kb. Since total probability should be 1, integrating equation 3 over phase space of all subsystems with different energies, we obtain the value of A as A is equal to 1 over integration of all the subsystems, space of all subsystems minus epsilon s divided by kb t and t gamma s. Here we have used the fact that integration of t omega s because d omega s integration of d omega s is equal to 1 because the total probability should be equal to 1. Therefore, the probability density takes the normalized form where we have removed the subscript and s in the denominator while it acts like a dummy index in the denominator inside integration. And this is the probability that the subsystem has energy epsilon. This is also called Boltzmann distribution function. For discrete spectrum of energies, this is written as rho equal to a to the power minus epsilon divided by kb t divided by summation I e to the power minus epsilon I divided by kb t. We can also write it in terms of partition function. Partition function can be defined as z. This is represented by z equal to I e to the power minus I epsilon I divided by a b t or integration e to the power minus epsilon s divided by k b t d gamma s. Hence, the term in the denominator is actually the partition function. This is partition function. So we can write probability density in terms of partition function as E equal to e to the power minus epsilon divided by k p t divided by z. Or if we write more correctly, we can replace rho with rho as a function of epsilon because it represents the probability that the system has energy epsilon. Subsystem has energy epsilon. I hope you have understood the lecture well. If you have any question, ask in comment section.